physics suggests something extraordinary. Beyond the dimensions we move through each day may lie entire hidden directions, stacked and folded beyond sight. Tonight on The Galaxy Scientist, we'll drift toward the idea of a 10th dimension, letting the mind wander softly where normal space cannot. If this calm exploration feels right to you, a gentle like and subscribe help others find their quiet space too. Rest easy now, and let's step into the unseen together. Imagine a single line, a quiet stroke of light drawn across the darkness. It stretches without end in both directions, never bending, never thickening, just an endlessly thin path. In this soft, imagined space, that lonely stroke is the first dimension. It knows only length. It carries no height, no depth, no room for anything to rise above or sink below. You could travel along it forever and yet remain held to that narrow track, like a thought that refuses to turn. Now let that lonely line be joined by another, crossing it like a gentle whisper at an angle. Where there was only one direction, now there are two. A sheet begins to appear in your mind, a flat and delicate surface that can spread wider and wider. This is the second dimension, a world of length and width woven together. Creatures that lived only on that plane would slide forward and back, left and right. But the idea of above and below would be as strange to them as a dream they could not quite recall. Depth would be an unfamiliar word, a concept just beyond their reach, like a color they had never seen. Then, softly, you allow a new direction to open. Something lifts away from the flat sheet. The world that felt like paper begins to swell into a volume you can almost touch. This is the third dimension, the home in which we spend our days. Here, depth steps in beside length and width, and suddenly there is room for height and thickness, for hollows and mountains, for rooms and rivers and rising towers. Buildings can stretch upward, valleys can sink deeper, and the universe takes on texture and shape. The spaces you walk through, the cup you hold, the sky that seems to arch above you, all of them belong to this three-dimensional stage, quietly cradling the stories of your life. But there is another presence, quieter and more elusive, that has always been there with us. It does not point north or east or upward. You cannot lean into it the way you lean against a wall, and yet it carries everything you have ever been. That presence is time, the fourth dimension, flowing steadily through the three-dimensional world. It is invisible, but it is never absent. It threads your childhood to your present, and your present to the moments that have not yet arrived, like a soft river moving through everything you know. Every laugh, every silence, every choice you have made is carried along that subtle current. In this gentle framework, every event is not just somewhere, but also somewhen. A conversation, a falling leaf, the turning of a distant galaxy, all of them sit at a point in space, and on a point along the river of time. The fourth dimension does not wander back and forth the way you can wander across a room. It has a direction, a quiet insistence. It carries us from what has already happened, through what is happening now, and onward into what will one day be. That one-way motion gives the universe a sense of story, of before and after, of cause and consequence. As we let our thoughts rest in that idea, the fabric of reality starts to feel richer. Space and time stop being separate boxes and begin to feel like threads woven together in one vast cloth. Behind the familiar surfaces of daily life, nature seems to hint at something more. In the deep language of physics, there are suggestions that our four-dimensional tapestry might be nested inside an even larger structure, that there could be additional directions curled so tightly or arranged so subtly that our senses glide over them without noticing. These higher dimensions would not simply be decorative. They might be essential for the way the universe holds itself together, for the way forces act, for the way matter and light behave. If we could somehow step sideways into those hidden directions, the world might look as strange and beautiful to us as our three-dimensional spaces would to a flat, two-dimensional being. Even if we cannot see these extra directions, the equations that describe the smallest particles and the largest structures sometimes whisper their presence. It is as if the cosmos is giving us a quiet, sideways smile, inviting us to consider that what we call reality is only a thin slice of something deeper. To move gently toward that understanding, people have spent centuries asking patient questions, letting curiosity sit beside uncertainty without demanding quick answers. Long before there were observatories or particle accelerators, there were thinkers sitting under oil lamps or starlit skies, wondering about space itself. Ancient philosophers closed their eyes and tried to imagine what it means for something to exist, what it means for there to be here and there. Were there invisible realms beyond what the senses could reach? Could the world be built from hidden structures, from forms that no hand could touch? Their answers were often poetic and incomplete, but their questions opened doors that others would later walk through with new tools and new languages. As generations passed, curiosity slowly hardened into more structured study. Geometry became a language, letting people describe lines, planes, and shapes with care. Measurements of the heavens grew more precise, and yet one feeling persisted, that space and time were two different things. Space seemed to be the stage. Time seemed to be the ticking clock beside it, counting beats while the play unfolded. Then came a new way of seeing that stage. A mathematician named Hermann Minkowski suggested that space and time are not separate after all, but parts of a single, interwoven whole. Instead of thinking about 3 dimensions of space and a lonely, independent time, he invited us to picture a 4-dimensional fabric he called space-time. In that view, every event in the universe is a point in this fabric, defined not only by where it happens, but also by when. A star being born, a comet passing close to a planet, a hand reaching for another hand, all of them become tiny marks in this woven continuum. On that foundation, Albert Einstein built his theory of general relativity, reshaping the way we understand gravity. Instead of imagining gravity as an invisible pull reaching across empty space, he described it as the gentle bending and curving of space-time itself. A planet does not fall around a star because it is being tugged by some unseen hand, but because it is following the natural curves in the fabric of the universe. Space and time together form the landscape, and matter and energy tell that landscape how to bend. In return, the curved landscape tells matter and light how to move, guiding them along paths that feel straight to them, even as those paths arc and swirl through the larger structure. From the soft musings of ancient philosophers to the bold revolutions of Minkowski and Einstein, the story of how we think about dimensions is really a story about our longing to understand where and when we truly are. Step by step, we have learned that the 3 dimensions our bodies move through are not the whole story. To really listen to the universe, we have to include the 4th dimension, time, as an equal partner, as real and as necessary as length, width, and depth. Time, when viewed as a dimension, becomes more than a background. It becomes part of the structure that defines everything. Unlike the 3 spatial directions, which let you wander in many ways, time carries a gentle arrow. It moves us forward, never backward, from memory into possibility. You can revisit a place, walking the same road or sitting in the same room, but you can never quite revisit a moment. Even if the scene looks the same, you are not who you were, and the universe has shifted in countless quiet ways. The coffee is a little cooler, the light a little different, the thoughts inside you arranged in new patterns. You can feel the importance of this dimension in something as simple as planning to meet a friend. First, there is the where. Without thinking too much about it, you move through the 3 spatial dimensions, choosing a corner of a cafe, a bench in a park, the entrance of a quiet library. Those choices are all about position in space. Left or right, here or there, near or far. If you and your friend choose different places, no meeting will ever happen, no matter how close in time your lives come. But there is also the when. Without naming it, you are working with the 4th dimension. You might say late afternoon, or a particular hour, or after the sun has set. If you arrive at the same place but at different moments, you will miss each other, just as surely as if you had gone to different streets. Space and time must both line up for 2 lives to briefly share one point. Only when both the place and the instant agree does the quiet miracle of a meeting appear. Physicists have a gentle picture for this idea. They speak of a world line, the path that an object or a person traces through space-time. It is like a thread drawn through the fabric of the universe, showing where and when that being has been, and where and when it may go. Your own world line winds from your earliest days to this very instant, passing through all the rooms, streets, and faces that have ever been part of your story. If you could step back and somehow see it, it would look like a single, unbroken curve, looping and weaving through the 4-dimensional fabric. For 2 people to truly meet, their world lines must cross, not just in space, but in space and time together. That crossing point is more than a dot on a map. It is a space-time event, a tiny intersection where both the where and the when match for both of you. Among all the countless possibilities in the vast continuum, there is that one shared moment where paths touch, where greetings are exchanged, where something new can begin. This way of thinking does not just apply to simple human encounters. It stretches outward to embrace the motions of the cosmos itself. Planets trace their world lines as they circle their stars. Stars trace their own through the quiet turning of galaxies. The Earth's path around the Sun is not only a loop in space, but also a flowing curve through time, with every position along its orbit linked to a unique instant. Each season, each sunrise, each turning of the planet is a bead on that long thread, a marker on the Earth's journey through space-time. When we accept time as a true dimension, something deep in our picture of the universe begins to soften and shift. Space stops feeling like a frozen stage decorated with moving pieces. Instead, everything becomes part of a single, unfolding story written into space-time. The universe is no longer a still photograph, but a slow, continuous film in which every frame is connected to the next. It gently urges us to look beyond static images of space and to sense the living, ongoing unfolding of events. And within that larger story, time, in its quiet way, lets us feel our own lives differently too. The moments of a day stop looking like scattered snapshots and begin to resemble sentences in a paragraph, each one leaning softly into the next. Every event carries traces of what came before it and offers something to what will follow. Cause and effect turn from hard labels into gentle links in a chain. tying our experiences together until they make sense as a whole. Seen this way, reality is no longer a stack of separate scenes, but a continuous narrative stretching from the distant past toward the still unwritten future. Letting time join the family of dimensions has done more than change how we imagine things. It has reshaped the foundations of physics. When Albert Einstein followed this idea to its depths, he discovered that time does not tick with the same steady beat for everyone, everywhere. Instead, it can slow down or stretch out, depending on how fast you are moving or how strong the pull of gravity is where you are. The old idea of a single, universal clock, quietly counting the same seconds for all beings in all corners of the cosmos, began to fade. In its place appeared a gentler picture. Each observer carries a personal tempo of time, a rhythm shaped by their own path through space-time. This is not just a poetic metaphor. It has been tested with extraordinary care. Physicists placed very precise atomic clocks on fast-moving airplanes and left identical clocks resting on the Earth below. After the journeys, when they compared them, the clocks did not agree. The difference was tiny, far too small to feel in an ordinary life. But it was real. Time had passed more slowly for the clocks that spent their hours racing through the sky. The same effect shows up in satellites orbiting above us. Their clocks must be constantly corrected so that our navigation systems remain accurate. Relativity, once a bold suggestion written in ink, now lives inside the devices that guide our travels every single day. In the world of the very small, time plays a different but equally mysterious role. Quantum mechanics describes particles not as simple, solid dots, but as spread out possibilities. At each moment, their state is described by a wave-like pattern of chances. And as time moves, that pattern shifts according to the Schrödinger equation. Instead of saying, the particle is exactly here, moving exactly this way, the theory tells us how likely it is to find it in one place or another, with one behavior or another. When we look, superposition lets a single particle exist in many potential states at once, while entanglement ties the fates of particles together, even when they are far apart. In all of this, time is the soft axis along which the story of these probabilities unfolds. Because time flows differently in relativity and sits at the very heart of quantum evolution, any attempt to build a single, unified description of nature must grapple with it. The smooth, curved space-time of general relativity and the jittery, probabilistic world of quantum mechanics do not yet fit together perfectly. To try to bridge that gap, physicists have turned their attention toward a daring thought. Perhaps our four-dimensional world is only part of something larger. Perhaps there are more directions, more ways to move, more subtle structures hidden just beyond the reach of our senses. This is where higher dimensions begin to enter the story. Going beyond the fourth dimension opens a realm in which our ordinary experience is no longer a reliable guide. The laws we thought we knew may still hold, but they are extended, refined, or reshaped by the presence of directions we cannot see. In the search for a theory that unites the graceful geometry of general relativity with the deep rules of quantum mechanics, many researchers have wandered into this higher dimensional landscape. There, the fabric of the universe becomes more intricate, with hidden folds and curls that might explain some of the puzzles we face. The fifth dimension and those beyond it are not just playful inventions. In several theoretical frameworks, they are essential ingredients. In string theory, which is one of the leading candidates for a unified description of nature, the basic building blocks of reality are not point-like particles, but tiny, vibrating strings. Each mode of vibration gives rise to a different kind of particle. the way different notes emerge from the same instrument when a string is plucked more gently or more firmly. For this picture to work, however, the strings cannot live only in our familiar 4 dimensions. The mathematics suggests that they require additional dimensions, as many as 10 or even 11 in some versions. These extra dimensions are thought to be compactified, curled up so tightly that we cannot perceive them directly. A common image is to imagine an ordinary garden hose lying on the ground. From far away, it looks like a simple line. You might walk past it and think it has only one direction along its length. But if you kneel down and look closely, you see that the hose also has a circular direction wrapped around it. An ant walking on the hose can move forward and backward, but also around and around. To the ant, the hose offers 2 dimensions, while to a distant observer, it appears to have only one. In a similar way, the universe might contain hidden directions, so small and tightly wound that to us, it seems as though they are not there at all. Because we cannot step into these hypothetical dimensions, we lean on analogies to feel our way toward them. One of the most vivid is the story of the Flatlander, a being whose entire life unfolds in a 2-dimensional world. This Flatlander can move forward and backward, left and right, but has no concept of up or down. Those directions do not exist within their experience. Their houses are lines drawn into shapes on a flat surface. Their bodies are outlines that slide past one another without ever truly passing over or under anything. Now imagine that a 3-dimensional sphere drifts gently through the Flatlander's world. At first, when the very bottom of the sphere just touches the 2-dimensional plane, the Flatlander sees only a single point, a tiny dot appearing from nowhere. As the sphere sinks deeper, the intersection between the sphere and the plane widens into a circle, which grows larger and larger. To the Flatlander, it looks as though a circle has appeared, swelling steadily. When the sphere continues on its way, the circle shrinks again, returning to a dot before vanishing completely. The Flatlander has no access to the full 3-dimensional object. All they can see is a shape that appears from nothing, changes size in a baffling way, and then disappears. To us, the mystery is simple. A higher dimensional object passed through a lower dimensional world. But for the Flatlander, it would be almost impossible to imagine the true form of the visitor. In many ways, we are like that Flatlander. If a higher dimensional structure brushed against our 4-dimensional reality, we might only see strange shadows or fleeting effects. We would witness events that seem to arise from nowhere, unfold in unusual patterns, and then slip away without realizing that they are the faint traces of something larger moving through a space we cannot picture. String theory suggests that our universe might be something like that. The particles and forces we observe may be the visible edges of deeper structures vibrating within a higher dimensional space. The extra dimensions are not empty decoration. They shape how the strings can vibrate and, as a result, determine the kinds of particles and interactions that can exist. In this quiet way, hidden dimensions could be responsible for the very character of our cosmos, from the strength of gravity to the behavior of light. When people talk about the 5th dimension in this context, they sometimes describe it as a space of possibilities layered over our own universe. One gentle way to picture it is to imagine all the different ways our universe could unfold, given the same starting point. Think of the birth of our cosmos as the trunk of a great tree. From that trunk, countless branches extend, each one representing a different way. Events might play out different choices, different chances, different paths, taken or not taken. To us, stuck on one branch, reality feels singular and fixed. But a being able to move freely in the fifth dimension would see the entire branching structure at once. It could wander from branch to branch, exploring alternate histories and futures that all grow from the same root. If we take another soft step outward, the sixth dimension invites us to imagine not only different outcomes, but different rules. In this view, each universe is like a thin sheet of paper. On one sheet, the laws of physics are just like ours. On another, gravity might be slightly stronger. On a third, certain particles might not exist at all. All of these sheets share the same initial conditions, the same opening moment, but evolve under distinct sets of rules. Stacked together, they form a kind of higher dimensional volume. A being who could move through this sixth-dimensional volume would not only see many possible futures of one universe, but many universes that began the same way and were then sculpted by different laws. The seventh dimension carries us even farther into abstraction. Here, we are no longer confined to universes that share our initial conditions. Instead, we consider universes that begin in completely different ways. To find an image for this, it can help to think of a vast, quiet library. Each book on its shelves is a universe. Inside one book is our story, with our familiar Big Bang, our particular arrangement of matter and radiation, our slowly forming galaxies and stars. In another book, the opening chapter is entirely different. Perhaps it begins without a familiar explosion. Perhaps space never expands, or expands in a way we would not recognize. Perhaps there are no atoms, no light, no structure at all. In some of these books, the laws of physics may resemble ours. In others, they may be unrecognizably strange. Some universes might race toward a quick, featureless end. Others might linger in long, delicate balance. Some might never give rise to complexity, while others might overflow with it in forms we cannot imagine. The seventh dimension is like standing in the middle of that library, aware not just of many outcomes of a single story, and not just of many variations with different rules, but also of entirely distinct beginnings, each one giving rise to its own complete reality. In that quiet hall of possibilities, among all those shelves and pages, the mind comes to rest on a simple, humbling phrase: universes with different initial conditions. From that quiet library of beginnings, where each universe rests like a closed book on an endless shelf, it is natural to wonder what it would feel like to move freely among them. If there were a being that existed in 7 dimensions, it would not be bound to a single story the way we are. It could drift through that library as easily as you walk through a room, slipping its awareness from book to book, page to page. For such a being, each universe with its own unique opening conditions and its own distinct laws of physics would be another place to visit rather than an unreachable idea. Infinite variations of reality would unfold before it like a calm, unending panorama, each one complete, each one different, all of them accessible. When we imagine the 8th dimension, the picture becomes even more intricate. Instead of thinking in terms of separate books on separate shelves, we can picture a vast, shimmering web. Each thread in this web is a timeline, the unfolding of one particular universe from its birth onward. Along these threads, there are special points, little crossings or knots, where something significant happens, where a choice is made, where a fluctuation tips the balance, where a new branch of possibility opens. These crossings are the nodes of the web, places where a single history can divide into many futures. In this 8th dimensional view, the entire web is present at once. All the timelines of all the universes that share a certain broader structure are woven together, their threads touching and parting, bending and recombining. A being with access to this dimension could move not only from one universe to another, but also from one key event to another, tracing how a tiny change in one moment might echo through the long fabric of time. It could explore the connections between different histories, noticing patterns that stretch across many worlds. The rise and fall of galaxies, the blooming and fading of life, the quiet transformations of matter and light. All of these would appear as patterns in a single, interconnected tapestry of universes and their stories. As our thoughts climb toward the ninth dimension, the scope widens again. Here we are no longer looking only at webs of timelines stitched together under a chosen set of rules. Instead, we step into a space that holds all possible combinations of initial conditions and physical laws that could ever be. One way to feel this is through the gentle art of origami. Take a single sheet of paper with careful folds. You can turn it into a crane, a flower, a tiny boat, or a shape that resembles a star. Each fold changes the form, and each sequence of folds leads to a different figure, sometimes simple, sometimes astonishingly elaborate. In the ninth dimension, that sheet of paper becomes a metaphor for the raw potential of existence. Each fold is like a change to the laws of physics or the initial conditions of a universe, perhaps a different density of matter at the beginning, a different strength of gravity, a different number of spatial dimensions, a different pattern for how particles interact. Every distinct way of folding corresponds to a different universe, with its own structure, its own behavior, its own path. The ninth dimension does not choose one figure. It holds all of them at once, all the shapes that can be made, all the ways the paper can be folded, refolded, and transformed. A being that lived fully in the ninth dimension would not merely be able to travel from universe to universe within one particular web of histories. It would be able to experience the entire gallery of what can exist. It could touch universes that share nothing with ours, universes with strange beginnings and stranger rules, universes in which time behaves differently, in which geometry bends in unfamiliar ways, in which there may be no light, no matter, or patterns of complexity we can barely name. For such a being, the boundaries between realities would blur. Here and there would not just mean different locations in space, or even different points in time, but entirely different sets of existence. And beyond even that, there is the idea of the 10th dimension, often described as the pinnacle of this hierarchy, a kind of ultimate container for all possible realities. If the 9th dimension holds all the possible folds of the paper, all the possible ways to shape universes with different beginnings and laws, the 10th dimension is like the quiet space in which the paper itself exists, along with every pattern it can possibly take. It is the realm where all conceivable and inconceivable universes, all timelines, all outcomes, and even the absence of any universe at all, are gathered into one overarching possibility. To picture this, we can return to the image of a cosmic tree, but let it grow even more elaborate. Start at the trunk, where the first conditions are set, and the lower dimensions quietly define what is allowed. As you move upward, branches split and split again, each one representing a different sequence of events, a different timeline, a different way the universe's story can unfold. On those branches, leaves emerge. Each leaf is a single outcome within that story, a specific realization of what could happen. From trunk to branch to leaf, you pass from initial conditions to laws, from laws to events, from events to outcomes. Now imagine not just one tree, but all possible trees, grown from all possible seeds, under all possible skies. The 10th dimension is like the point that holds the entire forest at once, the place where every trunk, every branch, every leaf, every pattern of growth and stillness coexists in a single, subtle whole. It is the singularity of infinite potential outcomes, a space in which nothing is left out. Every path that can be walked is walked in some universe. Every choice that can be made is made somewhere. Every story that can unfold finds a timeline in which it does. In that sense, the 10th dimension suggests a cosmos that is almost unbearably rich. It whispers that all possible outcomes do not merely hover as abstract ideas, but are realized in some strand of reality, in some timeline, under some set of conditions. For us, living quietly in 3 dimensions of space and 1 of time, this can be a dizzying thought. Yet it is also strangely comforting. It hints that the universe, or the multiverse, as some would call it, is not limited to the thin path we see, but blossoms in directions far beyond our immediate perception. Thinking about these higher dimensions does more than stretch our imagination. It also touches the heart of modern physics and cosmology. The attempt to understand dimensions beyond our familiar 3 of space and 1 of time has profound implications. It challenges us to question what we mean by reality and what kinds of structures might exist behind the world we can measure. It may even hold the key to solving some of the most persistent puzzles in science. Right now, our understanding of the cosmos rests on 2 great pillars. One is general relativity, which describes the way gravity works on large scales. It tells us how stars orbit within galaxies, how galaxies drift within clusters, how the universe expands, and how space-time itself curves around massive objects. The other pillar is quantum mechanics, which reveals the behavior of particles and fields at the smallest scales. It shows us the strange rules that govern atoms, electrons, and the invisible forces they exchange. These 2 theories are both astonishingly successful within their own domains, but they do not yet fit together smoothly. When we try to apply them both at once to the interior of a black hole, for instance, or to the very first moments of the universe, they seem to speak different languages. A true theory of everything, a single framework that unifies them, has remained elusive. Higher dimensions may be one of the missing pieces that helps bridge the gap. In many approaches to quantum gravity and unification, extra dimensions are not an optional flourish, but a necessary part of the structure. They may also shine a gentle light on some of the deep mysteries that trouble cosmologists. Consider dark matter and dark energy names we give to phenomena we can measure but do not yet fully understand. Dark matter reveals itself through gravity, holding galaxies together, bending light from distant objects, yet it refuses to shine or interact in the ways familiar matter does. Dark energy, on the other hand, seems to be driving the accelerated expansion of the universe, pushing galaxies apart faster and faster over vast scales. Some physicists have suggested that these puzzling effects might arise, at least in part, from the influence of higher dimensions. In certain versions of the M theory, a framework that extends string theory, our universe is pictured as a 3-dimensional membrane, sometimes called a brane, floating in a higher dimensional space. There may be other branes nearby, each one a universe with its own contents and laws. The matter within those neighboring universes might not be visible to us, but its gravity could leak across the higher dimensional space, tugging on our own universe in subtle ways. What we call dark matter could, in such a picture, be the shadow of matter that lives on another brane, its presence felt only through its gravitational pull. Similarly, the behavior of black holes, their interiors, their boundaries, their mysterious relationship with information may look different, when viewed through the lens of extra dimensions. Some theories imagine black holes as higher dimensional objects, whose properties we only partially see, like the Flatlander's circle cast by a passing sphere. Thinking in more dimensions gives us new ways to pose old questions, and sometimes opens paths to answers that were hidden in lower dimensional thinking. Looking ahead, the implications extend beyond pure understanding. If we ever learn to truly work with higher dimensions, even in a limited, indirect way, it could transform how we handle energy and travel. The idea is still distant, wrapped in speculation, but it invites a kind of quiet wonder. Mastering the subtleties of extra dimensions might one day reveal forms of energy storage, transfer, or generation that we cannot presently imagine, methods that are clean, gentle on our world, and so abundant that scarcity begins to fade from view. In the realm of space exploration, a deeper grasp of the fabric of space-time could be equally revolutionary. Concepts like warp drives or tunnels through space-time, ideas that now live mostly in science fiction stories, are sometimes discussed in serious theoretical work as extremely challenging, but not strictly forbidden. If certain conditions in higher dimensional physics can be met, they remain far beyond our current capabilities, and perhaps will always be. But in principle, they hint that faster-than-light travel or shortcuts across the cosmos might one day move from dream to distant possibility. For now, they rest as delicate thought experiments at the edge of our understanding, small reminders that the universe might allow more than our present tools can achieve, and that some of the wonders we imagine could be theoretically plausible within higher dimensions. From the vantage point of our quiet, four-dimensional lives, the search for higher dimensions might sound like pure abstraction, but in the laboratories of our world, it is already underway. Deep beneath the surface of the Earth, and in vast rings of metal and magnets, researchers guide tiny particles along nearly perfect circles, coaxing them to incredible speeds. In places like the Large Hadron Collider at CERN, protons are made to race in opposite directions, then gently nudged into collision. In the briefest flicker of these encounters, energy condenses into new particles, some familiar, some fleeting, all of them carrying whispers about how reality is built. If additional dimensions are woven into the fabric of the universe, their presence might leave subtle fingerprints in these high-energy events. Certain particles could appear to bleed energy into directions we cannot see, as though something had slipped sideways out of our visible world. Other particles might show patterns in their behavior that do not quite fit within a purely four-dimensional picture. Physicists watch the data with patient eyes, sifting through torrents of information for hints that a hidden dimension has brushed against our detectors. Each small anomaly is examined, questioned, tested, in the hope that it might be the first clear sign that space is deeper than it seems. This experimental work is accompanied by another kind of exploration, one that unfolds in chalk dust, ink, and glowing computer screens. Theoretical physicists and mathematicians spend their days wandering through high-dimensional spaces that exist, for now, only in equations and diagrams. They study how fields and particles might behave if more directions were available, how gravity might spread out in higher dimensional volumes, how the shapes of compactified dimensions could influence the constants of nature that we measure in our laboratories. On the page, they can unfold dimensions that no human eye can ever directly perceive. And yet these abstract constructions sometimes predict patterns that can be checked against the real sky and the real data. To help the imagination along, artists and scientists use visualizations and animations that show the shadows of higher dimensional shapes in lower dimensional slices. A four-dimensional cube, called a tesseract, can never be seen in full by three-dimensional eyes, but its projection can be drawn and rotated, its edges bending and interlocking in ways that feel both strange and mesmerizing. These images are not the thing itself, any more than a shadow on a wall is the person who casts it, but they offer a gentle foothold. They let us sense, in the simplest way, how something with more directions than we are used to can cast intricate outlines into the world we know. From the simplicity of a single line stretching into space, through the spreading of a plane, into the solid presence of three dimensions, and onward through time into the fourth, our journey through dimensions has slowly climbed toward the unfathomable complexity of the 10th dimension. Along the way, we have found our intuition repeatedly challenged. Our minds are built to picture three-dimensional scenes, and anything beyond that tends to blur and slip through our mental fingers. Yet, mathematics allows us to describe properties and relationships in these higher dimensional spaces with surprising clarity. Physics, in turn, offers frameworks such as string theory and M-theory that suggest these additional dimensions are not just mathematical games, but real aspects of the cosmos. Every time humanity has expanded its picture of space, the world has shifted beneath our feet. There was a time when many people imagined the Earth as a flat expanse, the sky as a dome above it. The recognition that our planet is a sphere, gently turning in space, transformed not only navigation and astronomy, but also art, literature, and philosophy. It changed our sense of scale and belonging. In a similar way, embracing higher dimensions has the potential to broaden our horizons once more. It invites us to rethink what it means to live in a universe that might be only a tiny slice of a larger, layered reality. This expanded view can ripple outward into every corner of human creativity, inspiring new stories, new images, new ways of asking who we are and where we fit. Out of this widened view of space-time and dimensions grows another dream, one that for many years seemed to belong entirely to the realm of science fiction, the dream of a warp drive. It is an idea that appears to defy the laws of physics as we commonly understand them, and yet it keeps returning, like a star that refuses to fade from the cultural sky. The thought is simple to state and breathtaking to contemplate. What if there were a way to travel to the farthest reaches of the cosmos without being bound by the usual limits of distance and time? What if the light years between stars could be crossed not in ages, but in spans that feel almost gentle by comparison? Stories have long imagined ships that leap effortlessly between star systems, but some physicists have wondered whether a carefully shaped understanding of space-time might, in principle, allow for something faintly similar. Instead of forcing a spacecraft to accelerate until it nearly matches the speed of light, perhaps there is another route, one that does not push the ship through space so much as reshapes space around it. In this picture, time and distance become less like rigid barriers and more like a fabric that can be stretched, compressed, and curved to make new paths. One of the most evocative formulations of this idea came from a physicist named Miguel Alcubierre, born in the year 1964 in Mexico City. As a young student, he was captivated by the mysteries of the universe and the elegance of Einstein's general relativity. His curiosity carried him from his early studies in Mexico to the University of Wales, where he immersed himself in the study of cosmology and the geometry of space-time. Later, while working at the Max Planck Institute for Gravitational Physics in Germany, he allowed his imagination to walk alongside his equations, and he asked himself a question that sounded as if it had been borrowed from a television script. The question was this: Could the equations of general relativity permit something that resembled the warp drives of science fiction, at least in theory? Inspired in part by the starships of the Star Trek universe, Alcubierre set out to see whether the fabric of space-time itself could be manipulated in such a way that a region of space carrying a spacecraft could move faster than light relative to distant stars, without the spacecraft locally breaking the cosmic speed limit. In the year 1994, he presented a model that seemed to say yes. In the Alcubierre concept, the spacecraft does not roar forward under its own engines. Instead, it sits inside a kind of bubble, a compact region of space-time that is being pushed and pulled by the geometry around it. In front of this bubble, space-time is compressed, like waves bunching up at the bow of a moving ship. Behind it, space-time is stretched, like the water spreading out in a trailing wake. From the point of view of distant observers, the bubble appears to move, carrying the ship along with it. But from the point of view inside the bubble, the spacecraft can remain almost at rest, cushioned in a calm region where the familiar rules of time and speed still apply. This is the subtle magic of the idea. Einstein's theory forbids objects from moving through space-time faster than light in their immediate surroundings. But it does not forbid space-time itself from expanding or contracting. We know from cosmology that space can stretch on cosmic scales, carrying galaxies away from each other at effective speeds greater than the speed of light, without any galaxy locally breaking the rule. Alcubierre's warp bubble borrows that behavior and folds it into a local, engineered form. It imagines riding not on a mechanical engine, but on a wave of space-time itself. To make this more tangible, you can picture the spacecraft as a small boat resting peacefully on the surface of an ocean. Instead of fitting the boat with a powerful motor, you reshape the water around it. A large wave rises behind the boat, lifting and pushing it forward, while a trough forms in front, drawing space inward. The boat does not need to churn against the water, it simply rides the wave. In a similar way, the warp bubble would carry the ship, letting the ocean of space-time do the work. However, this beautiful picture comes with heavy conditions. The particular shape of space-time required to form and stabilize a warp bubble is not something that ordinary matter and energy can easily create. In Alcubierre's solution, the bubble demands what physicists call exotic matter, with a negative energy density relative to the normal vacuum. This is not the kind of matter that makes up stars, planets, or people. Negative energy has appeared in certain quantum effects, such as the Casimir effect between closely spaced plates, but only in extremely delicate, tiny amounts. Scaling such phenomena up to the level needed for a warp bubble is a challenge of an entirely different order. This requirement is one of the major obstacles that stands between the Alcubierre drive as a graceful set of equations and any hope of building something real. Even if the laws of physics allow such configurations in principle, our current technology has no clear way to assemble or control the necessary distributions of energy. The mathematics that describes the warp bubble also implies staggering energy demands. Early estimates suggested that to generate a bubble large enough to carry a modest spacecraft, one might need an amount of energy comparable to converting the entire mass of the observable universe into pure energy. That phrase is easy to say and impossible to truly picture. The observable universe contains countless galaxies, each with billions of stars, each star far more massive than our Sunday. To imagine all of that mass turned into energy and then focused into a single engineering project is to step far beyond anything that could be called practical. It emphasizes how vast the gap is between an elegant theoretical solution and the tools we currently hold in our hands. For now, the energy and mass requirements sit like a high, sheer cliff between the dream of a warp drive and the grounded reality of our technology. A barrier that is, at least for the moment, far beyond our current technological capabilities. In spite of these towering obstacles, the story of warp drive does not end at the first impossible number. The landscape of theoretical physics is always shifting, always being gently redrawn by new ideas. Over time, researchers began to ask whether the warp bubble really had to be shaped exactly as Miguel Alcubierre first described it, or whether a different geometry might soften the energy demands. One especially hopeful step came when a physicist named Chris van den Broek suggested a subtle modification to the bubble's shape. Instead of imagining a large, thick bubble enclosing a wide region of space-time, Van den Broek proposed a configuration in which the interior volume, the part where the spacecraft sits, could be made relatively roomy, while the outer ring that does most of the space-time distortion is shrunk dramatically. By reshaping and folding the bubble in a clever way, his calculation suggested that the energy requirement could be reduced from something beyond comprehension to something merely colossal. In some estimates, the needed energy fell to the equivalent of a few suns, perhaps on the order of 3 stellar masses rather than the mass of the entire observable universe. That is still staggering, far more than any civilization like ours could hope to command, but it feels closer, like a mountain that has shifted from an infinite wall into something that, in imagination at least, might be climbed. It shows that even within the boundaries of the same basic theory, small changes in geometry can have enormous effects on what is possible. The warp bubble is not a rigid object. It is a shape in space-time, and shapes can be refined. Yet, energy is only one part of the difficulty. The other great barrier lies in the strange substance that the warp bubble seems to require: exotic matter with negative energy density. In Alcubierre's model, this exotic matter is not an optional decoration. It is essential. It is what keeps the bubble from collapsing, what holds the compressed and expanded regions of space-time in the right configuration. Without it, the carefully designed wave in space-time cannot hold its form. Negative energy, in this context, is a subtle and unsettling idea. It is not merely the absence of energy, not an empty bank account that reads as zero, but a kind of less than nothing in the bookkeeping of the universe. When we say that a region has negative energy density, we mean that, compared to the ordinary vacuum, the energy there is lower than what we usually call empty space. This strange deficit can change how space-time curves, sometimes pushing rather than pulling, acting with a kind of repulsive gravitational effect. It helps to distinguish this from a more familiar use of the phrase negative energy in classical physics. When we talk about gravitational potential energy, say, a small object in the gravitational field of a planet, we often assign it a negative value. The idea is that it would take work to move the object infinitely far away, to a place where its potential energy would be defined as zero. As long as the object remains bound to the planet, its potential energy is counted as negative. This convention is a useful accounting tool, a way of comparing different states. It tells us about how much effort is needed to separate things. But it does not mean the object is made of a strange new substance. The negative energy that appears in the Alcubierre drive is of another kind entirely. It is not simply a way of writing down gravitational binding energy. It is a proposed property of a real physical field, something whose energy density is truly less than that of the surrounding vacuum. Such a field would bend space-time in unusual ways, and in the warp drive solution, it is precisely this kind of bending that allows the bubble to form. In the known physics of our universe, there are a few delicate hints that such negative energy densities can exist, at least briefly, and in very controlled circumstances. One often cited example is the Casimir effect. When two uncharged conducting plates are placed extremely close together in a vacuum, quantum fluctuations of fields between them are restricted in a subtle way. The result is a tiny attractive force pushing the plates together, as if the vacuum between them has slightly less energy than the vacuum outside. In certain interpretations, this can be viewed as a small region of negative energy density, arising from the strange structure of quantum fields. But these effects are minuscule, glimpsed only in careful laboratory measurements. The amount of negative energy involved is so small that it is like comparing a single grain of sand to a mountain range. Scaling such phenomena up to the enormous levels needed to shape space-time around a starship is a challenge that belongs, for now, more to dreams than to engineering. Some researchers wonder whether quantum field theory places deep limits on how much negative energy can exist and how long it can persist. Limits that might render warp bubbles impossible in practice, even if they remain allowed in the equations. These difficulties, the need for vast amounts of energy, and the dependence on exotic matter we do not yet know how to create or control, show just how monumental the task would be to turn the Alcubierre drive from a beautiful mathematical possibility into a tangible reality. They are not just technical problems waiting for clever machinery. They are questions that cut to the heart of what the universe permits, to the ways its most basic forces can, or cannot, be shaped by conscious beings. Even if those hurdles could somehow be overcome, the warp drive concept faces another deep issue, one that is less about resources and more about the structure of space-time itself. This is the horizon problem, a quiet but serious challenge lurking in the design of the bubble. In astrophysics, a horizon is a boundary beyond which events can no longer influence an observer. The most famous example is the event horizon of a black hole, the invisible surface that marks the point of no return. Once something crosses that boundary, it cannot send signals back to the outside. Light is trapped, and with it any message or influence. To an outside observer, anything inside the event horizon is hidden forever. It might as well have slipped out of the observable universe. In the Alcubierre warp drive, the bubble that carries the spacecraft has a similar feature. The edge of the bubble acts as a horizon, a boundary beyond which information cannot easily pass. Inside the bubble, the spacecraft is cocooned in a region of nearly flat space-time, protected from the fierce warping taking place just outside. The walls of this cocoon, where space is being compressed in front and stretched behind, form a kind of shell that separates the interior from the rest of the universe. This separation is both the source of the warp drive's power and the root of its trouble. The same mechanism that allows the bubble to move faster than light relative to distant stars also isolates its contents. Imagine yourself inside such a warp bubble. Out beyond the horizon, the universe rushes by, distorted and unreachable. The bubble is doing exactly what it was designed to do, reshaping space-time so that you cover immense distances in a surprisingly short time. But because of the way the geometry works, no signal from inside can reach the region in front of the bubble in time to influence its motion. Your commands, your navigational adjustments, your attempt to tap the brakes, all of them would be trapped inside with you. Communication from the outside in faces similar difficulties. Just as nothing can escape from beyond a black hole's event horizon, nothing from beyond the warp bubble's boundary can easily slip inside in the way we would need to steer and guide the journey. The result is unsettling. A spacecraft traveling in this manner would be like a sealed seed caught in a fast-moving current, unable to change its course or even see clearly where it is going until the ride is over. Inside this warp bubble, The passengers would not be able to send instructions to the surrounding space-time to say, "Turn slightly left," or "Slow down now," or "Stop at this star." Nor could they receive updated information about unexpected obstacles ahead or last-minute decisions about destination. Once the bubble is formed and set in motion, its path would be determined by the initial conditions of the space-time distortion. The ship would be embarking on a kind of one-way journey, without the possibility of mid-course correction from within. The implications of this horizon problem are significant. It suggests that a warp-driven spacecraft, at least in the simplest versions of the model, would not be a nimble explorer threading its way between stars, but more like a projectile launched along a predetermined trajectory. That raises immediate practical questions. How would we ensure that the chosen path misses planets, asteroids, and other hazards? How would we guarantee arrival at a precise destination rather than somewhere vaguely nearby? And what would we do if something unexpected appeared in the way? When the bubble offers no means of gentle adjustment. To make warp travel truly useful, one might need a network of structures or devices outside the traveling ship, capable of creating, guiding, and collapsing warp bubbles from a distance. Instead of the spacecraft generating its own space-time wave, it might rely on an external infrastructure, perhaps stations positioned across interstellar space, or massive generators orbiting stars that can sculpt and direct the warp geometry from the outside, where signals and controls are not blocked by the horizon. In some visions, this begins to resemble an interstellar highway system, with prepared routes along which ships can ride, much as trains follow tracks laid down in advance. Such an arrangement, while imaginative, adds yet another layer of complexity to an already daunting challenge. It would require not only mastering the physics of warp bubbles and exotic energy, but also building and coordinating a vast network of devices scattered across the emptiness between stars. Each of these would need to operate with exquisite precision, shaping space-time gently enough to be safe, yet powerfully enough to be effective. It is a vision of engineering on a cosmic scale, where the very roads between worlds are carved into the geometry of reality itself. An awe-inspiring thought that, at the same time, adds another layer of complexity to the already difficult task of realizing warp drive technology. Even with all these difficulties, it is gentle but important to remember that the obstacles we have met so far do not, by themselves, break the idea of a warp drive at its roots. The horizon problem, as serious as it is for engineers and travelers, does not overturn the mathematics that allowed Miguel Alcubierre to write down his solution in the first place. Within the quiet, strict framework of general relativity, the basic principle remains sound. Space-time can, in theory, be curved and shaped into a moving bubble that carries a vessel along, while the vessel itself never locally outruns light. The equations still hold their calm, even if our technology trembles far behind them. As we let our thoughts linger on the warp bubble, another difficulty begins to drift into view, like a distant storm on an otherwise smooth horizon. This is the radiation problem, and it comes in two closely related forms. One part has to do with what builds up in front of the bubble as it pushes through the thin fog of interstellar space. The other part reaches inward, toward what might happen at the edges of the bubble itself, where space-time is curved so sharply that it begins to resemble the edge of a black hole. First, imagine the warp bubble gliding faster than light relative to the stars around it. Even in the emptiest stretches between suns, space is not truly empty. There are lonely atoms, Stray dust grains, pale streams of cosmic rays, tiny particles and faint radiation scattered through the dark. In ordinary flight, a spacecraft meets these travelers one by one, but a warp bubble, by its nature, reshapes the space-time it passes through. Particles and light waves that cannot outrun the advancing front of the bubble have nowhere to go. They begin to gather, like driftwood piling up at the bow of a moving ship. Over time, this accumulation at the leading edge of the bubble could become intense. Each trapped particle adds a little energy. Each bit of radiation increases the strain, until the front of the bubble carries a compressed, sharpened knot of energy along with it. As long as the bubble keeps racing forward, that knot moves with it, held in place by the very geometry that makes the journey possible. The real danger arrives when the bubble finally slows or comes to a stop. At that moment, the carefully arranged space-time around the ship relaxes. The warp bubble collapses back into more ordinary space, and with it, the accumulated radiation and particles are released. All at once, the energy stored at the front could burst outward, a sudden flash or wave sweeping past the ship and into its surroundings. The intensity of that release might be enough to bathe the craft in dangerous radiation, damage instruments, or even harm any world or station unlucky enough to be near the arrival point. Instead of arriving gently, the vessel might emerge with a literal shockwave of its own making. If we then turn our attention inward, toward the boundary of the bubble itself, a second worry appears. The sharp curvature of space-time at the bubble's edge resembles, in some ways, the conditions near an event horizon, the boundary of a black hole. In the 1970s, Stephen Hawking showed that quantum effects near such horizons should lead to a faint, steady glow of radiation, now called Hawking radiation. It arises from the way quantum fields behave when stretched across regions of space-time with extreme differences in gravitational pull. Virtual particle pairs that would normally appear and vanish together can, near a horizon, be split, one falling inward, the other escaping outward as real radiation. In the context of a warp drive, the intense warping around the bubble might create a similar stage. The geometry could, at least in theory, give rise to Hawking-like radiation tied to the bubble's horizon. If that is the case, then the interior of the bubble, which is supposed to be a safe harbor for passengers and equipment, might be slowly flooded with high-energy particles and light. Instead of a quiet cabin carried safely through bent space-time, the ship might find itself in a bath of harmful radiation, a kind of slow cosmic drizzle that could, over long journeys, become dangerous. Both aspects of the radiation problem run deeper than simple engineering headaches. They sit at the intersection of general relativity and quantum field theory, where our understanding is still incomplete. To protect passengers and destinations from accumulated radiation at the bubble's front, we would need ways to dissipate, deflect, or safely manage energy that is being gathered by the warp geometry itself. To shield those inside the bubble from Hawking-like effects, we would need a clearer, more unified picture of how quantum fields behave in such exotic space-time structures. Until we gain that understanding, any design for a warp drive would have to carry question marks where its life support plans ought to be. The implications are sobering. These radiation issues do not merely call for thicker walls or better shielding. They challenge the feasibility of long-duration travel under warp, and they remind us that bending space-time is not like bending metal or fabric. It means working directly with the rules that govern energy, information, and the vacuum itself. Ensuring the safety of passengers and the integrity of any craft making such a journey would require new insights into how quantum mechanics and relativity knit together and new strategies for coping with the harsh environment created by our own space-time engineering. If we step back for a moment and look at where the research stands today, we find a landscape that is both modest and quietly hopeful. Warp drive studies no longer belong only to the pages of fiction or the stray musings of dreamers. In quiet offices and shared online preprints, scientists are continuing to nudge the idea forward. Over the past decades, a stream of theoretical papers has revisited and refined the original Alcubierre model, probing its assumptions, adjusting its geometry, and searching for ways to tame its more extravagant demands. Building on work like that of Chris van den Broek, researchers have proposed new bubble shapes and configurations designed to lower the energy requirements further. By cleverly redistributing the regions of intense curvature, or by changing the way the bubble is thick in some directions and thin in others, some models suggest that the needed energy could be cut again and again, perhaps drifting toward levels that are still huge, but not wholly impossible to imagine in the far future. Each new proposal is carefully tested against the equations of general relativity, checked for hidden instabilities, and examined for unintended side effects, like excessive radiation or causality problems. At the same time, there are small but sincere efforts to look for experimental footholds. One of the better-known names in this area is Harold Sonny White, who has been associated with exploratory work at what was once called the NASA Eagle Works Laboratories. While we are still unimaginably far from building a true warp engine, such teams have investigated tiny, tabletop experiments aimed at probing how small space-time distortions might be created or measured. They analyze how certain electromagnetic configurations could, in principle, mimic aspects of warp geometries, and whether any measurable effect might hint at practical paths forward. These projects are delicate and often controversial, but they represent a willingness to let theory and experiment touch, even faintly. Other researchers, recognizing the difficulties tied to negative energy, have begun to explore alternative frameworks. Some ideas draw on solitons, solitary waves that travel without changing shape, familiar from water channels and optical fibers. In certain gravitational or field equations, soliton-like solutions can form stable, moving distortions. If a warp bubble could be modeled as a gravitational soliton, there might be ways to sustain it without the same extreme reliance on exotic matter, or at least to soften that requirement. These are early, fragile thoughts, but they broaden the range of possibilities. There is also growing interest in how quantum mechanics might help stabilize or even generate warp-like structures. Researchers are investigating the role of quantum fields in curved space-time, looking at how entanglement, vacuum fluctuations, and other subtle effects could influence the behavior of a warp bubble. Some speculate that carefully arranged quantum states might provide the negative energy densities needed, or at least contribute to them in a controlled way. Others study how quantum corrections to general relativity might change the picture of horizons and radiation, perhaps easing some of the problems we have already seen. Alongside all this, theorists are paying close attention to causality, the ordering of cause and effect in a universe that allows such strange geometries. Warp drives, if mishandled in the equations, can create space-time loops that seem to permit time travel, opening the door to paradoxes. Recent work has focused on identifying and ruling out configurations that would break the causal structure of space-time, or on understanding how deeper physical principles might quietly forbid them. Like a careful gardener pruning back branches that grow in dangerous directions, these studies aim to keep the warp drive concept rooted in physical law rather than fantasy. Taken together, these efforts paint a picture that is neither breathlessly optimistic nor dismissive. The warp drive remains, for now, a speculative idea, resting far beyond our current reach. Yet it also sits within the same mathematical and physical frameworks that have so successfully described black holes, gravitational waves, and the expansion of the universe. Little by little, through patient calculation and cautious experiment, researchers are trying to see whether this idea can be brought closer to the realm of genuine possibility, or whether it will ultimately be gently set aside as something the universe allows only on paper. As our thoughts return to the larger horizon, we find ourselves standing at a quiet crossroads. On one side lies the familiar, where rockets and ion drives inch us outward at speeds that feel small compared to the distances between stars. On the other side lies the dream of bending space-time itself, of riding waves in higher dimensional seas. Which path the future will favor is not yet known. The realization of warp drives, a concept that once lived only in stories and speculative visions, now rests on the slow accumulation of insight, the careful testing of bold ideas, and the emergence of tools and techniques we have not yet imagined. In the soft light of that uncertainty, one thing becomes clear. Bringing such drives into being depends on several key developments and breakthroughs. All those towering ideas about warp bubbles and space-time waves bring us back, very quietly, to a simple truth. Before anything can leave the drawing board, the theory beneath it must be gently made sound. The first steps toward any warp technology live not in metal or reactors, but in equations and deep understanding. We would need ways to soften the enormous energy requirements, to imagine new geometries that ask less of the universe. While still doing what we hope, we would need to learn how to create and stabilize these delicate bubbles in space-time, without tearing their fabric apart. And we would need to understand how to manage the radiation and strange quantum effects that arise when we bend space-time so sharply, keeping travelers safe inside their own bold experiment. That means progress in places that already feel mysterious. In quantum mechanics, where particles flicker through probabilities. In the study of exotic matter, whose very name hints at how little we know. And in our ability to handle energy, not just as fuel, but as something we can shape in subtle, precise patterns. Only when these strands are woven together, understanding, control, and imagination, does the idea of a warp drive begin to drift from pure theory toward the faint possibility of practice. And then there is everything that does not fit into an equation. If a warp drive were ever to move from chalkboard to starship, it would carry with it a bundle of ethical and practical questions. Crossing the space between stars at unprecedented speeds would change exploration in a single breath. Distant systems that are now just glimmers in telescopes would become places where we could stand, sample the air, touch the soil, listen for alien winds. Our relationship with the night sky would shift from gazing outward to planning visits. With that power comes a quiet responsibility. Space is not empty of meaning. Worlds that seem barren at first glance may harbor fragile ecosystems, chemical dances that, given time, could tip toward life. Racing from star to star, we would have to ask ourselves how we touch those environments, how we observe without destroying, how we meet any extraterrestrial life, microbial or intelligent, with care rather than conquest. There is also the question of who gets to travel. If such technology ever became possible, would it belong to a few nations or companies, or would it be treated as a shared bridge for all of humanity? Practically, a working warp drive could transform how we think about resources and research. We might learn to gather materials from asteroids and distant moons, to build observatories in quiet corners of other systems, to conduct experiments in environments that are impossible to create near Earth. It could open the door to interstellar colonies, small, patient communities, learning to live under alien suns. In time, our focus might shift from "we are visiting the cosmos" to "we live within it." In many places, space would no longer be only a frontier to be crossed, but a wider home to be tended. For now, these possibilities rest as gentle maybes at the edge of our dreams. We look up at the stars as they prick the darkness, and instead of seeing unreachable points of light, we begin to imagine them as destinations, some near, some impossibly far, all woven into a map that we might one day trace with our own hands. That imagined future, with its uncharted territories and quiet, careful journeys, keeps our curiosity awake. It beckons us to keep asking questions, to keep learning how reality works at its deepest levels. And beneath all our thoughts of bending space-time lies another, older wondering. Not just how to move through space faster, but what it really means to move through time. Imagine time not as a straight arrow, but as a vast, soft fabric, a canvas woven from moments. Every choice, every event, every heartbeat is a thread stitched into that cloth. It stretches endlessly in all directions, a past full of memories and forgotten days, a future branching into possibilities, a present where everything meets. What if, somehow, that fabric could be navigated? What if you could wander along its weave the way you wander through a forest path, stepping back toward an earlier moment, or edging forward into a future that has not yet solidified? What if history were not only something we look back on, but a landscape we could, in some careful way, walk through? Time rules our lives. We measure it in hours and years, plan around it with calendars and alarms. We chase it when we rush, and feel it chasing us when we grow older. Yet for all this, it remains one of the most mysterious elements of the universe. We can measure it, but can we touch it? We can feel its flow, but can we shape it? The idea of time travel has captured human imagination for generations, sometimes as comfort, sometimes as warning. It appears in bedtime stories and grand novels, in films and quiet conversations, always asking the same, unshy question: could time be more flexible than it seems? From the point of view of science, that question is both fragile and serious. If the laws of physics treat time as a dimension, as real and fundamental as the three of space, then in principle it might be manipulated. Einstein's theories opened that door with a gentle but radical insight. Time is not universal. It does not tick the same way for everyone, everywhere. It stretches and compresses depending on how fast you move and how deep you sit in a gravitational field. In the curved space-time near a massive object, time itself slows compared to distant regions. The universe does not offer a single, absolute rhythm. Black holes make this especially vivid. They are regions where gravity grows so strong that not even light can escape once it crosses a certain boundary. Near that boundary, time warps dramatically. To an outside observer, anything falling toward the black hole appears to slow, its clock ticking more and more sluggishly, never quite seeming to cross the horizon. The same equations that describe this strange behavior also describe the gentle time dilation experienced by astronauts moving swiftly around a planet. We have measured that effect close to home. Astronauts aboard the International Space Station, circling Earth at high speed and in a weaker gravitational field than the surface, age ever so slightly more slowly than the people below. The difference is tiny fractions of a second over many months, but it is real and carefully confirmed. They return a whisper younger than they would have been if they had stayed on the ground. It is not the dramatic leap through ages that stories imagine, but it shows that time is not fixed. It bends. So the dream of time travel no longer belongs only to fantasy. It presses its nose against the window of science and asks to be taken seriously. Could these same principles that slow time for fast-moving travelers ever be pushed to an extreme, turning subtle dilation into something we would recognize as a journey into the future, or even into the past? If the fabric of space-time can be bent into warp bubbles, might it also be twisted into loops where yesterday and tomorrow touch? As soon as we ask these questions, paradoxes crowd around us. What happens if you travel back and change something that led to your own journey? Can cause and effect survive when the order of events is no longer clear? These puzzles are part of what makes time travel such a fertile playground for storytellers. They let us explore not only clever plot twists, but also deep questions about responsibility, destiny, and free will. Long before equations entered the scene, people looked to the sky and felt time in the slow turning of the heavens. Ancient civilizations watched the sun's path, the dance of the moon, the patient drift of constellations. They carved stones and built monuments that tracked seasons, solstices, and eclipses. They created calendars to predict the flooding of rivers, the arrival of spring, the right days for planting and harvest. For them, time was a cycle, a wheel turning under a dome of stars. Day followed night, winter followed autumn, and their stories reflected this rhythm. In the modern era, our fascination with time found a new canvas in stories, film, and literature. The idea of stepping outside our one-way journey and moving along time in other directions became a rich metaphor. In the year 1895, H.G. Wells wrote The Time Machine, a novel that did more than entertain. It gave us a simple, powerful image: time as another dimension through which a machine could travel, much like a train moves along a track. It offered the notion that the past and future might be places, in some sense, as real as any city. Decades later, films like Back to the Future took that idea and wrapped it in humor and warmth. A stainless steel DeLorean car, an eccentric scientist named Doc Brown, a fictional device called a flux capacitor. All of these became icons in the collective imagination. Through them, a new generation felt the thrill of leaping between eras, of seeing parents as teenagers, of discovering how small choices ripple outward through time. The fascination is not limited to one language or culture. In Japan, stories like Steins Gate weave time travel into tales of friendship, sacrifice, and fragile timelines. In the former Soviet Union, films such as Ivan Vasilievich Changes Profession, played with the whimsy of a modern man, dropped abruptly into the days of a long-gone Tsar. Across the world, storytellers have used time travel to explore not only adventure, but also regret, hope, and the bittersweet desire to fix what once went wrong. Why does this theme reach so deeply into us? Perhaps it is the dream of rewriting history, of returning to a moment we wish had unfolded differently and nudging it toward a kinder outcome. Perhaps it is the excitement of the unknown future, the temptation to peek at the chapters ahead. Or perhaps it is something more quiet, a blend of nostalgia and anticipation, a longing to revisit cherished instants and to glance, just for a moment, at the promises of tomorrow. As our scientific understanding grows, the questions become sharper. If our theories hint that time is pliable, even in small ways, then the gap between story and possibility narrows. We stand at a strange threshold, where fiction and physics look at each other across a dimly lit room. Could we ever build paths through time that are more than metaphors? Should we, if we could? And what responsibilities would we bear if we gained such power? In quiet lecture halls and late-night offices, the blackboard becomes the place where these questions are gently tested. On that smooth, dark surface, symbols and lines become bridges between imagination and reality. Equations like E=mc² are written in careful chalk strokes, and for a moment, they are not just marks. They are keys, condensed expressions of how mass and energy relate, how space-time curves, how the universe stores and trades its contents. We look at those keys and wonder, in the hush between one line of chalk and the next, they can unlock the stars. But can they unlock the secrets of time travel? From cinema screens to quiet living rooms, time travel has worn 1,000 different costumes. We have seen heroes step into glowing machines, race down tunnels of light, or simply blink and find themselves in another century. But if we gently peel away the layers of special effects and music, there is a quieter question waiting underneath. Is there anything in our real universe that could make time travel more than a story? To approach that question, we can return to the idea of space-time, the four-dimensional fabric that Albert Einstein helped us see. In this picture, space and time are not separate backdrops, but threads woven together into one continuous cloth. Mass and energy, stars, planets, even you sitting where you are can bend and stretch this cloth. Gravity is not an invisible tug, but the way space-time curves around what exists. When that fabric bends, the paths of light and matter bend with it. We have grown used to this idea when thinking about orbits and black holes, but it has a quieter implication too. If the fabric can be curved, perhaps time itself can be made to flow differently along different paths. Time dilation is the gentle name we give to this effect. According to relativity, time does not move at the same rate for everyone. How quickly your clock ticks depends on two things: how fast you are moving and how strong the gravitational field is around you. When you move very quickly through space, your motion through time slows compared to someone who remains still. When you sit deep in a gravitational well, close to a massive body, your time also slows relative to someone far away. This is not just a beautiful idea written in equations. It has been carefully measured. Astronauts aboard the International Space Station, circling our planet at high speed and in a slightly weaker gravitational field, age more slowly than people on the ground. The difference is tiny, a fraction of a second over many months, but it is real. Particles whipped around in powerful particle accelerators live longer than they would at rest, their internal clocks slowed by their near light speed motion. Atomic clocks flown on airplanes and carried up mountains fall out of perfect sync with identical clocks left at sea level. Everywhere we look closely, the universe whispers the same message. Time is flexible. If time can be stretched in this way, the mind naturally wonders, could it ever be twisted? Could there be tunnels, shortcuts, or loops through space-time that link distant points not only in space, but in time as well? Relativity allows for a strange class of objects called wormholes, hypothetical tunnels that connect two different regions of space-time. On paper, these are like bridges in the fabric, narrow throats that join distant points and, in some solutions, different moments. They are speculative, fragile creatures in our equations, but the mathematics does not simply forbid them. It suggests that, under certain conditions, such structures might be possible. At the same time, the physics of the very small quantum mechanics waits in the background like a patient, quiet companion. Some scientists have wondered whether quantum effects could play a role in making certain forms of time travel possible, or at least in softening the harsh edges of space-time needed for such feats. Others point toward black holes, those dark giants whose gravity is so strong that not even light can escape near them. Space and time are twisted dramatically. For an object skimming close to a black hole and then escaping, far more time might pass elsewhere than for the traveler. It is tempting to ask whether such extreme environments might serve as gateways, not only to other regions of space, but to other times. The scientific community does not speak with one voice on these matters. Time travel touches the foundations of physics, from the nature of reality itself to the rules of cause and effect. Some models that allow loops in time also threaten to produce paradoxes. Others suggest that deeper principles, perhaps in quantum gravity, will quietly forbid such structures, even if relativity alone seems to permit them. There is no consensus, only a slowly evolving conversation. Still, one direction of time travel already lies gently within our grasp. Travel into the future, not in the dramatic, cinematic way of stepping into a machine and vanishing from this year, reappearing in a distant century, but in a quieter, more patient way that uses time dilation itself as the vehicle. Think of time as a river that flows at slightly different speeds in different channels. According to relativity, the faster you move through space, the slower your personal time flows, compared to someone who remains still. If you could move close to the speed of light, your minutes and hours would slip by more slowly than the years ticking away on Earth. From your perspective, your heart would beat at its normal rhythm, and your days would feel ordinary. But when you returned, you would find that far more time had passed for those you left behind. This is the essence of the famous twin paradox. Imagine two twins who begin together. One stays on Earth, living an ordinary life under familiar skies. The other boards a spacecraft and travels through space at speeds close to the speed of light, turning around after a long journey and coming home. When the traveling twin steps out of the ship, they would find their sibling older, perhaps much older than themselves. The paradox is only apparent when we carefully follow the paths each twin takes through space-time. The mathematics shows that their clocks genuinely tick at different rates. The traveling twin has, in a real and measurable sense, jumped into the future. In reality, we are far from building ships that can reach such extreme speeds. The energy required to accelerate even a modest spacecraft to a significant fraction of the speed of light is enormous. The stress on any physical structure and on any human body inside it would be immense. Engineers and scientists are exploring advanced propulsion concepts, fusion drives, light sails pushed by powerful lasers, antimatter engines in theory. But each one brings with it daunting technical and safety challenges. Even so, the principle remains. If extreme speed can be achieved and survived, then forward time travel, at least, is not science fiction, but a consequence of the laws we already know. It is strange to imagine a future in which time dilation capsules might one day exist, vehicles designed not to carry us simply from place to place, but from now to later. You could step inside, endure a journey at near light speed, and emerge in an era where cities, languages, and technologies have all moved on. Perhaps people would use such journeys to escape looming disasters, to leap over difficult centuries, or to glimpse civilizations far beyond our own. But such possibilities raise gentle, heavy questions. If you can leave your own time behind, what does that mean for your ties to others? If knowledge of the future becomes available to some, will it feel like a gift or a burden? And what of free will? If someone travels into the future and brings back stories of what they have seen, do those stories become a fixed script that everyone else must follow? Or are they only one possible path, subject to change as choices are made? These questions do not have simple answers. They sit at the border between physics, philosophy, and the quiet landscape of individual hearts. While one path to time travel leans on speed, another continues to wind its way through the strange geometry of space-time. Wormholes. These hypothetical tunnels have captured our shared imagination, from science fiction novels to scientific journals. In essence, a wormhole is a shortcut. Instead of moving through normal space along the long curve between two stars, you step through a narrow throat that connects them, as if you had folded space so that distant points touch. A common image is to imagine a sheet of paper with two dots drawn far apart. If you travel only along the surface, you must walk the whole distance between them. But if you gently fold the paper so that the dots meet and then push a pencil through both, you create a new connection, a direct passage between places that were once far apart. In the analogy, the paper is space-time, the pencil is the wormhole, and the fold is the bending of the universe's fabric. The idea gained an extra measure of scientific attention in part through the work of writers and physicists together. When author Carl Sagan was crafting his novel, Contact, he wanted a believable way for a character to cross vast interstellar distances quickly. He consulted physicist Kip Thorne, who explored whether general relativity could allow a traversable wormhole. Their collaboration helped popularize the idea that such structures were not purely fantasy, but had a place in real equations, even if their physical realization remains deeply uncertain. Einstein's general relativity does allow solutions that look like wormholes. The mathematics describes them as bridges in space-time, linking distant regions. However, these solutions often come with a catch. The wormholes tend to be unstable. Left to themselves, they pinch off and collapse so quickly that nothing can pass through. To keep them open long enough for a person or even a beam of light to travel, something must counteract the intense gravitational forces pulling them closed. Once again, exotic matter and negative energy appear in the story. In some theoretical models, introducing regions of negative energy density near the throat of a wormhole could exert a kind of repulsive effect, pushing outward against collapse. If such matter could be arranged just so, it might hold the wormhole open, making it traversable. In principle, by carefully choosing how and where the wormhole connects different regions of space-time, one could build not only a spatial shortcut, but a link between different times. In that sense, wormholes could be, at least in theory, tools for time travel. Popular media often skips over these fragile details. On screens, wormholes are usually shown as stable, swirling portals, luminous vortices that open on command and stand patiently while ships glide through. The underlying complexities are compressed into a few glowing rings of light, a visual symbol of mystery rather than a portrait of finely balanced geometry and exotic physics. The real picture, if wormholes exist at all, is likely to be far more volatile. Tiny changes in energy, matter, or quantum fluctuations could cause them to wobble, flicker, or collapse. Despite the lack of direct evidence that any wormhole has ever formed naturally, the topic remains a lively area of research. Scientists use computer simulations to study what would happen if wormholes were present in the universe, how they might appear in the bending of light from distant stars, or in the motion of matter near their mouths. They explore different shapes and stability conditions, asking what kinds of exotic fields would be needed to keep them open, and whether those fields can exist within the bounds of known physics. Through these careful, imaginative efforts, they hope to understand not only whether wormholes can exist, but what their properties and potential uses might one day be. If wormholes truly exist and could be tamed, the possibilities for time travel would be almost dizzying. One mouth of a wormhole might be held gently in our present moment, while the other is carried by motion or gravity far into the future or left behind in the past. Step through one side, and you would emerge not only somewhere else, but someone else. In that picture, a wormhole becomes more than a shortcut through space. It becomes a bridge across eras. You could imagine scientists sending instruments into the future to watch how a star will evolve, or into the past to study ancient cosmic events up close. You could even imagine attempts to warn distant descendants or prevent global catastrophes before they unfold. But with that power comes a heavy, quiet question. Are we ready to hold something like this in our hands? A wormhole that links different times does not only raise technical concerns, it touches responsibility. What changes would we dare to make if we could step into yesterday? What events would we feel justified in nudging, and which would we be wise to leave untouched? Wormholes pull us toward questions not simply of where we might go, but when and whether our wisdom can keep pace with our ingenuity. To look for deeper clues, we can let our gaze fall from the vastness of wormholes down into the tiny, shimmering domain of the quantum world. This is the realm where particles sometimes act like waves, where outcomes are not fixed until we look, and where reality itself feels more like a cloud of possibilities than a solid, single track. It is strange and delicate, and yet it underlies everything around us. If there is any place where the rules of time might be more flexible, it could be here. Quantum mechanics challenges our everyday sense of how things should behave. Consider the famous double-slit experiment. When tiny particles, such as electrons, are sent one by one toward a barrier with two narrow openings, and then allowed to land on a screen behind it, we might expect them to form two simple bands, as if they were tiny bullets choosing one path or the other. Instead, over time, they build up an interference pattern, a series of light and dark fringes, like ripples overlapping on a pond. It is as if each particle passes through both slits at once, behaving like a wave that spreads out and interferes with itself. Only when we force ourselves to watch which slit it uses does it begin to act more like a classical particle again. This dual nature suggests that, at the quantum level, the fabric of reality is soft and malleable in ways our everyday experience does not prepare us for. Great minds, such as Richard Feynman and Niels Bohr, spent their lives exploring these mysteries. Quantum mechanics has become one of the most successful theories in all of science, predicting the behavior of matter and energy at extremely small scales with astonishing accuracy. Yet even as it works beautifully, it leaves us with questions that feel almost philosophical. What does it mean for something to be in many possible states at once, and only later choose one? Some physicists have wondered whether these same principles could offer a foundation for time travel. Quantum tunneling, for instance, allows particles to appear on the other side of barriers they do not seem to have enough energy to cross, as if they had slipped ghost-like through a wall. In everyday life, a ball rolling up a hill will come to rest and roll back if it cannot reach the top. But in quantum mechanics, there is a small chance that the ball will be found on the far side anyway, having tunneled through the hill. If space can be crossed in this surprising way, it is tempting to ask whether time could be tunneled through as well, at least in some subtle or indirect sense. Quantum computing adds another layer to the story. By harnessing superposition and entanglement, quantum computers can, in principle, explore many possible solutions to a problem at once, performing certain calculations far more quickly than classical machines. Some speculate that as these devices grow more powerful, they might be able to tackle the incredibly complex equations that describe warped spacetime, wormholes, and closed time loops. Problems that are now too tangled for us to solve might someday yield to algorithms running on quantum hardware, revealing whether exotic time travel geometries are truly allowed or whether hidden constraints forbid them. Then there is the phenomenon that Albert Einstein once called spooky action at a distance, quantum entanglement. When two particles are created or prepared together in a special way, they can become entangled, forming a single shared quantum system. Measure a particular property of one, say, its spin and the state of the other is instantly fixed, no matter how far apart they have drifted. Change the setup for one, and the correlations in the other adjust to match, as if an invisible thread connects them across space. At first, Einstein disliked this idea because it seemed to suggest that information might travel faster than light, violating one of the core limits in his theory of relativity. Over time, however, experiments confirmed that entanglement is real and fundamental. The key subtlety is that, while the correlations appear instantly, no usable message can be sent faster than light this way. The randomness of each individual result protects the speed limit, even as the joint pattern of outcomes reveals an eerie connection. Could this sort of instant influence play a role in time travel? Most physicists think entanglement alone cannot create a time machine. It cannot be used to send information into the past in any straightforward way. Still, the interplay between quantum non-locality and the structure of space-time is an active area of research. Some scientists explore mathematical models of quantum loops in time, or closed, time-like paths at the quantum level, to see whether probabilities and causality can remain self-consistent even when events appear to circle back on themselves. There are also ideas that link quantum theory to the early universe, where gravity and quantum effects may have been tightly intertwined. In such extreme conditions, the distinction between before and after might blur in ways we do not yet fully understand. Some speculative interpretations suggest that quantum superposition could be connected to multiple timelines or branching realities, a picture in which all possible outcomes of certain quantum events coexist, each in its own branch. In these views, one might poetically imagine a person existing in a superposition of paths, some closer to the past, some leaning into the future. Whether any of this will someday add up to practical time travel is unknown. For now, the meeting point between quantum mechanics and time is a hotbed of careful speculation and subtle mathematics. The questions themselves, however, are part of the journey. Could the principles of superposition and entanglement someday help us understand not only how matter behaves in time, but how time itself might be shaped? From the tiniest scales, our attention can drift outward again to the grandest structures we know, black holes, those dense, silent suns turned inward, whose gravity is so intense that nothing, not even light, can escape once it falls too close. If anything in the universe might twist time into a loop, it seems natural to wonder whether these dark giants could be involved. Here enters the idea of a closed, time-like curve, a path through space-time that eventually loops back to the same point in time where it began. Imagine walking along a trail that winds and circles until, without ever stepping outside the path, you find yourself back at yesterday afternoon instead of today. A closed, time-like curve is like that at the level of space-time, a world line that bends around so far that it reconnects with its own past. The concept was first explored in detail by the mathematician and physicist Kurt Gödel in the late 1940s. Gödel found a solution to Einstein's gravitational field equations, that described a rotating universe, a cosmos in which all matter spins together in a grand swirl. In that strange model, the rotation twists space-time in such a way that closed time-like curves can exist. In other words, there are paths through that universe along which a traveler could return to their own past. Gödel's model is fascinating, but in most physicists' eyes, not a realistic description of our universe. It requires conditions such as a global rotation of all matter together that do not match what we observe. Still, his work opened a door. It showed that the equations of general relativity do not automatically forbid time loops. Under certain arrangements of mass, motion, and geometry, the fabric of space-time can, at least mathematically, fold back on itself. This realization encouraged other scientists to search for more plausible scenarios. One candidate involves rotating black holes, often called Kerr black holes. Unlike a perfectly non-spinning black hole, which is described as having a point-like singularity at its center, a rotating black hole is predicted to have a ring-shaped singularity, a thin, loop-like region where densities and curvatures become extreme. Around it, space-time is dragged into rotation, a phenomenon known as frame dragging. In some models, the twisting of space-time near such a rotating singularity could, in principle, give rise to closed time-like curves. The ring might act as a sort of gateway to regions where paths in time loop back around. It is a haunting picture. Somewhere deep within the heart of a spinning black hole, time itself might be knotted, but that picture comes with a catch, and perhaps several. The intense gravitational and rotational forces inside such an object do not only twist space-time, they also create barriers. One of these is known as a Cauchy horizon, a boundary beyond which the usual rules for predicting the future from the present begin to break down. Past that horizon, the equations of general relativity can yield unpredictable, even divergent results. It is a region where the laws of physics, at least as we currently write them, lose their familiar grip. The study of closed time-like curves and black holes is full of such uncertainties and paradoxes. If these loops in time truly exist, they raise the possibility of cause and effect being tangled in unsettling ways. A traveler could, in principle, interfere with events that led to their own departure. Messages could be sent to prevent the very actions that created them. These puzzles have motivated some physicists to suggest that there may be deeper principles at work, rules not yet fully understood, that protect the universe from such contradictions. One proposal along these lines is sometimes called a chronology protection hypothesis. It gently suggests that the laws of physics themselves conspire to prevent the formation of closed time loops that would lead to paradoxes, perhaps by making any attempt to create them unstable, or by invoking quantum effects that disrupt would-be time machines before they can function. To even imagine drifting toward a rotating black hole is to imagine standing before one of the universe's most powerful and secretive engines. Its gravity twists space like a ribbon, its spin drags time into motion, and its center hides a singularity wrapped in shadow. If we ever found a way to approach such a region safely shielded from the crushing tides and fierce radiation, the question would linger like a held breath. What would wait on the other side? Would the curved heart of a Kerr black hole open into another era, another universe, or something stranger still, something beyond even our deepest equations? But black holes are not the only cosmic riddles that hint at paths through time. There is another idea, thin as a thread, ancient as the first instant after the Big Bang, known as a cosmic string. These hypothetical one-dimensional filaments are imagined as cracks or seams left behind in the universe's earliest moments, formed when the hot, newborn cosmos cooled just enough for its fields to shift and settle. If they exist, they would be unimaginably slender, narrower than an atom, yet carrying extraordinary density, with a gravitational pull strong enough to bend space-time sharply around them. Though still theoretical, cosmic strings have drawn the attention of physicists for decades. J. Richard Gott and William Hiscock explored how such strings might interact with space-time. Gott suggested that if a cosmic string were to move at nearly the speed of light, the distortion it creates could be so intense that space-time might fold into a loop, forming a path that leads into the past or forward into the future. In that picture, time is no longer a straight thread, but a curve that can be followed like a trail through the woods. Yet for now, cosmic strings remain elusive. To detect one, we would need to observe gravitational signatures on cosmic scales, patterns in starlight, distortions in galaxies, ripples in the cosmic background that lie beyond the sensitivity of today's instruments. And even if we did discover one, learning to harness it for time travel would be a challenge of staggering proportions. These strings, if they exist, are remnants of a universe far younger and more violent than the one we know. Approaching them, let alone manipulating them, would require a mastery of gravity, quantum fields, and energy that lies far beyond our current abilities. Still, they remain an intriguing possibility, especially when we think again of quantum entanglement. We have already seen how two particles, once entangled, behave as if distance does not matter. Touch the state of one, and the other responds instantly, even across astronomical space. It is a connection that seems to stretch beyond geometry itself. Some theories wonder whether such entanglement might also have a temporal dimension, whether entangled particles might share not only space, but time. Could information someday be transmitted not merely across great distances, but across eras? Imagine a future where a kind of quantum internet spans not only light years, but centuries, allowing instant communication between different points in history. For now, this idea sits gently on the speculative edge, but it draws researchers into fertile ground, asking how quantum laws might mingle with gravitational ones, and what secrets could emerge from their meeting. The frontier, where cosmic strings and quantum entanglement overlap, is one of the most mysterious landscapes in modern theory, a place where the enormous and the infinitesimal touch. Some imagine that if cosmic strings exist, and if entanglement could influence their behavior, then perhaps a bridge could be built between the quantum scale and the cosmic scale, a union that could reshape our understanding of time travel entirely. It would be like watching two different worlds, the delicate world of the very small and the powerful world of the very large, reach for each other across the silence of the void. But even if such paths through time were possible, we would face puzzles that cut to the bone of logic itself. Time travel confronts us with paradoxes, delicate knots in the fabric of cause and effect. These are not just philosophical curiosities. They determine whether time travel can exist in a universe that refuses to contradict itself. One of the oldest is the grandparent paradox. Imagine stepping into the past and preventing your grandparents from meeting. If they never meet, one of your parents will never be born, meaning you will never be born. But if you never exist, who traveled back to stop them? The paradox spirals into loops, each version canceling the next. To soften this contradiction, some theorists propose the idea of parallel universes. In such models, each action branches reality into a new timeline. You do not erase your own past, you simply create another, parallel version of it. Then there is the bootstrap paradox, named after the old phrase about pulling yourself up by your own bootstraps. Imagine traveling back in time with a book of Shakespeare's plays. and giving it to Shakespeare before he wrote them. He publishes the works, and centuries later you discover them, carry them back, and complete the loop. Where did the plays originate? Nowhere. They exist in a circle with no beginning, no origin point in creativity or history. Cause and effect blur into reflection. The very notion of authorship dissolves. Another troubling idea is the paradox of predestination. In this scenario, your attempt to change a past event becomes the cause of that very event. You travel back to prevent a disaster, but your presence or your actions inadvertently trigger it. The universe seems to catch your hand in mid-air, guiding your intention into the exact outcome you hope to avoid. This poses questions not just about physics, but about free will itself. Are we travelers in time with the power to rewrite fate? Or are we actors in a script whose pages cannot be altered? These paradoxes are not solved yet, but they are taken seriously by physicists and philosophers alike. They probe at the structure of space-time, asking whether the universe allows loops in causality, or whether deeper rules step in to prevent such contradictions. Some propose that any attempt to create paradoxes would fail through subtle physical effects, a self-consistency that quietly prevents the impossible. Others suggest branching realities, where each paradox resolves by splitting the world into new versions of itself. As we travel through these ideas, cosmic strings and quantum entanglement, rotating black holes and time loops, we find ourselves on a threshold. The possibility of time travel is no longer just a whisper from science fiction. Step by step, theory by theory, it draws closer to the edge of real science. Researchers continue to refine equations, build better instruments, and search for hints in the sky. Each discovery adds another thread to the tapestry. And yet, even as the edges of the unknown brighten, one question grows larger and quieter than all the rest. If we ever reach the point where time travel becomes real, if wormholes open, if loops form, if cosmic strings bend the hours like branches, are we prepared for what we might find? Are we ready to meet our future or our past face to face? Time waits for no one, but in some far possibility, subtle and shimmering, perhaps one day we might wait for time.